Hello, everyone, and welcome to another Into the Terminal. Today, we're going to be talking about regular expressions, or regex. And you'll notice that my co-court, Nate, is off today, so it'll be just me that you're saddled with. So bear with me as I do the producery things as well. There may be a couple of hiccups here and there where the screen share doesn't come in just right or what have you. So apologies in advance. All right, so regular expressions. We actually use them a ton. You may not have even realized that you're using them, but they can get absurdly complex if you want them to be. So why don't we just go ahead and jump on into the terminal and we can start learning about regular expressions. All right, so I mentioned that we do regular expressions all the time, right? So we use it with commands like grep. So if we're doing something like looking for a man page. Maybe I'm interested in looking for a man page that has something to do with memory, right? So I look for the keyword mem, and then I get all these things. So we could do stuff like pipe this to grep, and I can look for things that are in section 1 or 8, right? So I could grep for something like this, right? And these are the commands that are in section 1, which is regular user commands. And let me just go ahead and grep-v away all these gcloud things, right? So these are the, actually, let me switch that around. So we still get the nice highlighting of our grep. There we go. So these are the ones that are in section 1 of the man page. And I can change my regular expression to say, I want the things that are in parenthesis 8. And there's the parenthesis 8 things. But maybe you want to see both of these together. And so this is where we start to make a more complex regular expression, right? So regular expressions have the idea that you could say, I'm looking for this string of characters. I'm looking for a left parenthesis, the letter 8, and a right parenthesis. So that's why it's only showing me those lines that have that exact string. But we can start to put in additional characters in our regular expression to give it more flexibility. So for example, I can use a regular expression like this, which says, I'm looking for a left parenthesis, and then I'm looking for another character. But that character has to either be a 1 or an 8. And then that 1 or 8 is going to be followed by a right parenthesis. And so what we're still going to get is a match that is 3 characters in length, parentheses on either side, and then the central character is going to be either a 1 or an 8. Right? So we can see that it matches the commands that are 1 and 8. And so I use stuff like this all the time because I want to look up, maybe I forget the name of the command I'm looking for, but I remember it has something to do with system memory. And so this gives me a much smaller list than when we just did a man-k. Because man-k showed me things in section 3, which is programming libraries, or section 3PL, which are Perl module libraries. So I can more narrowly scope the information I'm looking for. All right, so quick sidebar trick. All right, so let's say that you're doing something like this, say process status, and you're looking for a specific program. So it tells me, here's all the HTTPD daemons, except there's also this one, right? Because my grep also has the string HTTPD in it, and so it also matches the data that's coming out of the process status. So if we were doing things like trying to take this list and cut it down to just process IDs and then send that somewhere, we would accidentally also send our grep process. So a quick trick that also uses this acceptable character set. Whoops, there we go. So notice when I put the grep string in the H in square brackets, what we're saying is I'm looking for a pattern. That pattern will be an H followed by a TTPD. But because the grep itself has square brackets, it no longer matches the pattern, right? Because it's an H square bracket HTTPD, which doesn't match the thing the regular expression is looking for. So that excludes it from these results, which then gives me a cleaner set of results for me to then use cut or like other applications on to make additional choices. All right. The last thing that we're going to cover in the critical pack is wildcards. All right. So let's say we're interested in some log data. Something happened on our machine and we need to look at logs, but only for a certain time. So if I do a less on var log messages, we can see that the logs have a very specific format, right? We get the date and then the 3 field time of hours, minutes, and seconds. So if I'm interested in something that happened during a certain time period, I can use a regular expression and say what pattern I am looking for. So let me go down to the bottom real quick. All right, so it runs from 1500 something to 1604 something. All right, so maybe what happened at between 1602 and 1604. So we can grep for August 1, 16, 0, 4, or 5. Oops, and I have to tell it the name of the file I want to look at. Did I not do that right? One quick thing. All right. Oh, there's an extra space. Aha. And it's not a 0, 1, it's just a 1. So let me change my real expression here. So maybe I want to not bind myself to this specific thing. I could say August space any character at all followed by a 1. So that way, if we end up having something like a 2-digit date, it'll still match. If it is a 0, it'll match. If it's a space character, it'll match. So this dot is an any character wildcard that we could put in our regular expression. Man, I'm still not doing it. 16, 0. Did I mistype something? Am I not doing syntax or case correctly? Let's do this. 16. Oh, it's because nothing matched in those things. Okay. So let's do 7, 6, 7, or 8. There we go. That seems a little bit better. Helps if you use a string that actually has matches. All right. So here we are. There's our time code that's being highlighted, right? And we can use our acceptable set of characters to match anything that happened at 1606, 1607, or 1608 in our output. We used our wildcard as well. So instead, I could just say if I wanted everything in the first 10 minutes, I could do a set 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, or I could just make this a any character wildcard. So it's a August 1st, 16:0 something. Right, and we can see that it matches 09, but it also matches 04 up here that wasn't in my original set of acceptable characters. Right, so the wildcard there is the period character. All right, but that means that things like IP addresses where a period is actually used can be problematic. And so when we switch to the deeper dive, we'll talk some more about syntax like uh, escaping things. We're also going to talk about stuff like how do you match more than one character, right? If I wanted to match anything that was in the 1600 hour, I might use something like this. But how do I like make even more wildcards without actually having to type individual dots a whole bunch of times, right? So we'll cover wildcards. We're also, or sorry, multipliers rather. We're also going to cover anchors, and then we'll put some of our newly acquired regular expression knowledge of how to craft a regular expression to use in some real life looking for data in files. All right, so we will be right back. Stay with us. Don't forget to mash that like and subscribe, and we will talk about more regular expressions in just a second. All right, so now is the time of the show where we'll be paying attention to the chat and answering questions that come in from the chat. If you're a deferred viewer, please feel free to leave a comment. Nate and myself do monitor comments and respond to them. All right, so when last we spoke, mere scant seconds ago, we were using a regular expression that looked like this, right? We had some wildcards, and actually I'm going to go ahead and put in my mix of extra characters like 79. We can use a set of acceptable characters as a certain character position. And then we can also do things like wildcards. So there are several different wildcards that one can use in regular expressions. Probably the combination you see most often is something like this. So a wildcard applies to the preceding, sorry, man, I keep saying wildcard. A multiplier, like star, applies to the preceding character. So in this case, modifying the dot character, but dot for regular expressions is a wildcard. And what I'm saying with the star is I want 0 to infinitely many of these preceding characters. So I'm essentially saying as many any characters as you want to match. We can also do something like this, where this question mark multiplier says I will accept 0 or 1 of the preceding character. So this means that there can be something following the 789, but it can only be one character that follows. Or there could be no character that follows the 789, and that will still match my regular expression. All right, so let me show you what this looks like with a star. All right, so you'll recall when I just used my regular expression before, it highlighted this date time code. But when I put in something like a dot star, let's see how it changes the highlighting. Interesting. So this is what the beginning part of my regular expression matches, this date and time thing. And then I said any character, but I could have 0 to infinitely many any characters. And so it pulls that 0 to infinitely many any characters into my match that it then displays with the syntax highlighting in grep. All right, but this would be important if we're doing things like global search and replace. If we're doing global search and replace, now this entire line matches my regular expression rather than a substring in the line. So you need to be a little bit careful with wildcards because they might match more than you expect them to match. Right? If I change that dot star to be a dot question mark, and there we go. You can see that my match now picks up this one character that followed the hours and minutes. And let me go ahead and do a logger. Actually, no, we're not going to do that. All right. So this question mark here applies to the one preceding character, which happened to be a wildcard, which would mean it would be any character is acceptable at this character position. I could also do something like I'm interested in semicolon. There we go. That'll work. So if I say I want a semicolon, notice that that doesn't match my data pattern. My data pattern is a colon. However, when I check, it's matching the same date character string, but notice that it no longer matches that one extra character in the back, right? Because in my regular expression, I said I would accept 0 or 1 of this character following that hours and minutes I'm looking for. And the matches that it shows me have 0 semicolons matching after the minutes of my text string I'm looking for, right? So when I say wildcards or multipliers means 0 or more, the 0 is also important. Now you could instead say, no, I really need to see just the lines that have semicolons after them minutes and hours. So instead of a question mark, you could say plus. That's another multiplier. But this multiplier says I require 1 or more of the preceding character. So now my regular expression is looking for August 1st, 16, 0, 7, 8, or 9, and at least 1 semicolon. But I could have infinitely many semicolons on the line as well, and that would also be okay. And what's going to happen is it's going to come back with no matches, right? Because all of my data doesn't have a semicolon at this position. It has a colon, and that doesn't match the regular expression that I designed that insisted that I have at least 1 semicolon after the minutes field, right? So you can also do a wildcard or a multiplier rather that's an exact number or a range of numbers, like I'll accept 3 to 5 of these characters that precede me. But yeah, like it can get complex. We could also do something like change this a little bit. So what the regular expression says now is I'm looking for August 1st, 16, colon, 0. And then the next character is going to be a 7, 8, 9, or semicolon. I need to have at least 1 7, 8, 9, or semicolon, but I can have more 7, 8, 9, or semicolons after that. Right, so here is one where that last thing, I had at least 1 7, 8, 9, or semicolon. In this case, it's a 9. Right, up here, I had at least 1 7, 8, 9, or semicolon. In this case, it's an 8. Right, so you can also do things like kind of customize your set notation to add these additional characters that you accept and then require 1 or more of them. All right, in the chat, I saw somebody ask, what's the backslash do? All right, so that's Nesdy. Nesdy asks, what's the backslash here? Oops, right there. Okay, so this is a function of how we're designing the regular expression for grep. So regular expressions and the syntax, like a plus is a wildcard, or sorry, a multiplier. Square brackets means a set of characters. A dot is a wildcard. That's all pretty standard regular expression syntax. The problem is that grep is going to be the thing that actually interprets that syntax. Or maybe sed, which is another thing that does regular expressions, is going to interpret that syntax. Or maybe your Python program is going to interpret the regular expression syntax. Or maybe Perl is going to interpret the regular expression syntax. And so when you're building the regular expressions, a lot of the core syntax remains the same, but then you'll see a little bit of weird stuff like the backslash here. So let me take out the backslash. And I bet what's going to happen is it will not match anything. Because without the backslash, grep is now looking for the literal character plus sign after our time date stamp information. So because none of my strings have a literal plus sign after the minutes, nothing matches this regular expression. And so in grep's syntax for regular expressions, the backslash basically tells grep, hey, I'm giving you something special that you need to pay attention to because it's got special special meaning. And so this is an escape. The backslash is an escape for grep regular expressions. We see this in the shell as well, but usually the backslash means it's a literal, meaning I'm not looking for the special invocation of this character. I literally mean this character. And in regular expressions, that's flipped for grep. I will tell you that Perl, for example, does not use backslashes to exempt special characters. In fact, it's the other way. The character retains a special meaning, and you have to use backslashes to say, no, I mean literally a plus sign at this location. So there is a little bit of implementation specifics difference between regular expressions in how they're used in different programs or programming languages. So there's some slight syntax deviation. But again, the core stuff, dots are wildcards. Pluses are one or more any characters. Stars are 0 to infinitely many any, or additional characters. Question marks are 0 or 1 preceding character. Using curly braces to denote an exact number you're looking for. That's all standard syntax that's used in regular expressions. All right. Cool. And I see that Billy Holmes in the chat also answered the question. Thanks, Billy. All right. So I wanted to talk to you a little bit about one more thing. And so you'll remember before, I put in something like this, right, where I said 0 to infinitely many any characters. And I said, oh, look, now your match matches the whole line. And that can be bad if you're going to send us data to something else to further process, because now you're not just sending the thing that was matched, potentially, you're sending this bigger string because that's all part of the match now. So it turns out that regular expressions, by default, use something called a greedy algorithm. So other algorithms, they'll actually be more conservative in what they match, and they'll say, okay, because you said 0 to 1 any character, I'll just stop looking after I find 1 character, right? Because that meets the criteria that you put in your pattern. But regular expressions employ something called a greedy algorithm, which means it's going to try and find the largest possible match that it can find. So even though this string would match my regular expression, the regular expression language tries to make a longer string match the requirement. And so it then says, well, does this match? Yep, that's 1 any character. Okay, well, can I get bigger? Well, does this match? Yep, that's 2 any characters. That's cool. Does this match? Yep, that's 3 any characters. That's fine, right? And so it keeps trying to make the match longer and longer and longer until it runs into a piece of syntax that causes the match to stop. And then it's like, all right, now I'm done. I've matched as big of a string as I can, and that's my goal. So there are options in some implementations of regular expressions. I've used this in Perl, for example, where it says stop after you meet your minimum criteria for a match. But by default, most implementations of regular expressions try to make as big of a match as possible. And that means that you need to kind of put some extra care into it, right? So maybe I'm interested in matching this whole date timestamp, and I can actually simplify my regular expression a little bit to say, I'm going to match 0 to infinitely many of these. Actually, I was going to say 1 to infinitely many of these characters. I'm going to accept 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and colon. right? Because there's a 1 through 9 colon, there's a 1 through 9 colon, there's a 1 through 9 colon, right? And I have a multiplier there, so I can just keep tacking on 1 through 9 colons until I get here. That's a space character. That's not a 1 through 9 colon. And so I've broken the string that I've been able to smush into my regular expression match. Right? So as soon as it reached something that fell outside of the regular expression criteria, it stopped matching. And that's another way that you can kind of limit the scope of your regular expression so that you can do a little bit more or less structured character ordering. And I can be very unstructured and say, hey, I just want something 0 through 9 and colons, or without using an overly matched or greedy match with a whole bunch of characters that I didn't intend. All right. So what's some other stuff that you can do? Because we need to get better at not just matching our thing, but maybe deciding where the thing matches. So I'm going to make a copy of a dictionary. All right, so I have this file called words. It's got all these words, right? It's got a lot. In fact, let's see. It's got 479,826 words in this words file. That's a lot of words. So maybe I'm interested in looking in this 400,000 lines of data for a specific pattern. Maybe I'm looking for the phrase ish, ISH. That's pretty common syntax. So we're going to look for that in words. All right, and it matches a whole bunch of things. And in fact, it matched 4,680 words. But notice that this ish, it like matched in the middle of the word. It matched at the end of the word. It actually like matches at the beginning if a thing starts with the word ish, right? So where this character set exists, anywhere on the line, as long as it's anywhere on the line, we're going to match it. And that's how we ended up with 4,680 matches to this character string. So maybe I'm interested in words that don't have the ish in their sounding somewhere, but instead that end in the ish sound, right? Because maybe I'm a linguist, and so I'm interested in these words because I'm a linguist. So what I can do is I can grep ish $ words. So the $ is another special character for regular expressions. It means end of line anchor. So ish is only going to match if the thing after ish is an end of line marker. Right? So we can see that now we're only matching those words that have ish at the very end. And in fact, we go from 4,000 words to 2,173 words. Similarly, we can, if we're looking for words that start with ish, instead of a dollar at the end, we can say beginning with a caret. So that's the beginning of line anchor. Right, so these are all the words that start with ish. That's a really small list. We can go further. We can actually bind both the beginning and end of line. So I could say this, which means I'm looking for lines in this file that begin with ISH and then have the end of line marker, of which there's only one match that matches this regular expression. All right, cool. We could also do something like I'm looking for things that end in fish and dish, right? So there's dish, there's fish. So we can use our syntax we already learned with things like acceptable character position sets to decide where it is. And then we wanted this ish to be at the end of the line. It's the end of the word. All right, but maybe I'm looking for things that end in ish, but I'm not really interested in fish. So here's where real expressions start to get a little bit crazy. So if I use this regular expression, it says I'm looking for an F followed by ISH and then a new line character. That's the exact opposite of what I said. I said I wanted things that did not have fish at the end. And so you can use a caret inside of a character position set. And instead of meaning beginning, like it did when we used it at the beginning of our search criteria, if it's used within a character position set, it's a logical not operator. So here I'm saying I'm looking for not F ISH words, right? So here we get Tish and Kish, right? But we're not seeing any fish words in there anymore. All right, so why is this important? Let me give you a silly example. So let's say we are doing a search and replace. So we're going to use a command like sed, and we're going to do an inline edit, and we're going to search for FISH $, because in our alternate reality, turns out scientists have been hard at work, and they've replaced fish with dinosaurs. All right, they actually like started monkeying around with DNA, and it turns out all fish in our alternate reality become dinosaurs. And so we have to, instead of calling them fish, we have to replace that with dino. Oops, and I want to do that on my word style. Right, so now when I look for words, I should see no fish at all, because I replaced them with dinos. But I'll still see things that have fish in the middle, right? Because in my search and replace, I specifically bound that replacement to be things where fish was at the end of the word. And if I now look for dino, right? We don't have yellow fish anymore, we have yellow dino. We don't have wolf fish anymore, we have wolf dinos, right? So this is how you do search and replace, for example. And this is where real expressions get really dangerous, because what if I didn't, in my search or replace here, use that end of line anchor? I meant to, but I forgot. Well, now all of the instances of FISH anywhere within the word got replaced with dino, right? So remember before when I grepped for fish, it was in there. We had things like white fishes was a word in there. Oops, and tell the file doesn't exist anymore because it got replaced with white dinos. So when you're inexact with your regular expression and you match too much, all of a sudden when you try to do other things with the data that matched, you might inadvertently mess up things you didn't mean to mess up. So that's where crafting like really crisp regular expressions that match just the strings you're interested in is important, because you take those matches and you send them somewhere else to do something else with them, like a global search and replace. What would happen if you were trying to global search and replace a variable definition within some code and you were inexact, and instead of one variable being swapped, a whole bunch of variables got swapped? That would be potentially really painful to try and undo. Or maybe you're doing something like going through a DNS record and changing the first 3 octets of an IP address to a new IP address range, but you were inexact in your match, and now you swapped too much stuff, and your DNS zone file doesn't work anymore because it doesn't have the right syntax in it, right? So that's why getting a match that matches exactly what you want is important. All right, cool. But wait, there's more. So we not only have the beginning and end of line anchors, like we just saw with my fish example, we also have beginning and ending of word anchors. Because a lot of times you don't have a file like this where there's a word per line. You have like a whole bunch of stuff on every line. And so you may be looking for a piece of text in the middle of some line somewhere. So for that, we have word boundaries. So what I'm saying here with this backslash angle brace is I want an end of word anchor after the CAT letters. So it's CAT, end of word anchor. Well, what's an end of word anchor? It is not characters, or I should say not alphabetic characters. So it could be a space, it could be a dash, it could be a period, it could be a tab. So anything that's not a through Z character, that's what's going to end up being in this word anchor that we're using. All right, so you can see that right here, right, there's my CAT, and then my end of word boundary is that dash. Right, we see these where there's CAT and then an end of word boundary, which in this case is a new line character. Let's see if there's any others that are interesting here. Oh, this one's interesting, right? CAT, end of word boundary, which is the single quote, right? So that's why it's performing these matches. All right, but maybe we're not interested in these kind of things where there's stuff in front of cat. I just want every instance of cat that's bound by a word boundary on either side, right? So you can put 2 word boundaries in. So I want a beginning of word boundary. That's the backslash less than or angle brace. And then I have an end of word boundary, backslash greater than angle brace. Right, and so now my match like this one, the beginning of word boundary is the beginning of the word. And then the end of word boundary is that non-A through Z character. Same thing with cat's paw, right? Beginning of the word is the beginning of the word boundary, and then the single quote is the non-A through Z end of word boundary. This one, dash, that's a word boundary character, right? It's not an A through Z, so that's what starts my match. And then the end of word boundary is the new line in this case. All right, you can also mix and match different types of anchors. So I could say something like this. So now I'm looking for a word boundary followed by CAT, followed by a new line. And so what that should do is all these guys up here that were still word bounded cat, but they weren't end of line word bounded cat, those should all vanish from my matches. Right, so now it's a word boundary and then a new line. And if it doesn't have a new line at the end, it didn't show up in my matches. All right. What else can I show you on regular expressions? We talked about multipliers. We talked about word boundaries. We talked about wildcards. Hmm. Well, I'll leave it open in the chat. If there's something that I've missed, please let me know. And what I'll do now is I'll transition to like using this in practice on real data. So we looked earlier at a log file, and I wanted to time bound my log file. I used a regular expression to pull out just the entries from the log that match a certain time criteria. And I actually use that a lot when I'm doing troubleshooting. When something happened at a specific time, like a service outage, or I start getting paged about something not working correctly, or notifications from monitoring, I should say. So there, it's like I have a time when it began. So let's look around that time for what happened in the logs on that file or on that machine. So that's something where when troubleshooting, I use those time barriers a lot to try and get to just a segment of log so I can look at stuff more specifically. I actually grabbed a couple of example log files here, like this one. So this is a web server access log, and it has a similar format of data throughout it. Right here is the address of who accessed my site. There's the time and date. This is the request, and then including the protocol. And then over here, this is the status, the size that was pulled, and then we get some things like the client, right? So this was a Mozilla browser, or a Mozilla-based browser. It looks like it's some kind of bot, right? We can see that this was mobile Safari or Chrome, right? So there's different things that that we'll see in this data. All right, so maybe I'm interested in this for all of the Android clients, right? We can see right here in the request that Android is a term that's in there, right? So we can do grep Android. So these are all the Android requests. But maybe we're interested in Android requests from a specific host, like this person. So that's where we get a more complex regular expression. So we could do something like this. So I'm looking for this IP address. Then there's going to be a whole bunch of characters, right? 0 to infinitely many any characters. And then I want the word Android. Right? So there's my IP address. And then the 0 to infinitely many any characters. And then Android at the end. But my IP address is a little bit suspect, because these dots that are in my IP address, those are actually any characters, right? They're the any character wildcard. So I might use this to say, I'm looking for exactly a dot character rather than the wildcard character that is normally interpreted for the dot, right? It won't change my output in this example, but if instead there were like series of numeric strings that happen to be similar to an IP address, you might find more than you were bargaining for. All right, how about we're interested in these Android requests, but notice that a few of them are response 200, meaning it's a successful request. So maybe I'm interested in things that are not 200. That's actually 2 zeros. How about 039? All right, so what we're saying is we're looking for our IP address. Then there's going to be some text somewhere in between on the line. And then I'm looking for a character that is not a 2 followed by a character that is a 0 through 9, followed by a character that is a 0 through 9, and then there's going to be more stuff, and then the word Android. All right, so let's see how we did here. Did not work very well because there's a 3-digit number that doesn't begin with a 2. And so here's my first part of the match. And then there's my 3-digit number that doesn't begin with a 2. And then there's the rest of my stuff until the word Android. Not quite what I was looking for. But notice that this right here is separated by space characters. So what if I go back into my regular expression and I just say, this 3-digit number I'm looking for that does not begin with a 2 has to have a space character on either side of it. All right, so here is one that looks like what I want, right? Because that is return code 302, which is a non-successful transfer. So you can see that you start to mix in different things into your regular expression syntax to kind of customize the thing that you're matching. And using wildcards, I mentioned this earlier, using wildcards like .star may match more than you bargained for. So you need to be a little bit more specific if it's overmatching what you're expecting. All right. Cool. Let's see what else I got here. I have this example log. Right, so example log is an application log. And what's interesting in this one is that it's got this state, like this priority of how important it is. So maybe I'm looking for grep for things that are not info. And then we're going to strip out the trace. Right, and this is what we have left. Looks like there's a bunch of events in here and blank lines. So maybe I'm interested in the events, but I'm not interested in all events. I'm interested in sender events. So here I did a little bit different, right? So I said, I know I don't want these things. So I use grep-v in a regular expression, which happened to be a very exact regular expression, to get rid of this data. Then I got rid of this trace data. And then I said, I'm only interested in sender. But notice that there's two things in there. There's sender and sender withdrawal. So what if I'm not interested in sender withdrawal? What could I use? The layperson would say, oh, yeah. Word boundary, right? That'll get me sender, but not sender withdrawal. Not word boundary. Because this underscore here, that's a word boundary character, right? It's not an A through Z. So instead, I think we want to look for end of line anchor sender entries, right? So we can pull out just those things we're interested in. Or maybe we're looking for close entries. Well, there's only one. So you can start to like hook together a whole bunch of different greps to get to the point where you then specify the data that you're really interested in. All right, let's see here. What else do I have? Apache log. So this one is interesting because it also has states, right? It has these error states. And so maybe I'm interested in getting the error messages. But that's not going to work because in regular expressions, square brackets, that's a single character set of acceptable characters in this position. So what I'd be looking for is a character that's an E, an R, or an O. So again, we're going to have to use some escaping to look for just the error things. All right, and then I'm also going to maybe make this a little more specific and say I'm looking for mod JK errors. And I'm not just looking for all mod JK errors, I'm looking for mod JK6 errors. Right, so I can use these wildcard combinations with multiplier to say, I'm looking for a bunch of text in between this exact string and my next exact string. Right, so I can pull out just those that I'm interested in. And then I could do something like even more specific. I'm looking for lines that begin with Monday, and then they'll have some stuff on them, and then it'll be 17 something. So I'm building out a more imprecise way of specifying things like time, right? So I want a begins with square bracket MON, right? Like this guy right here. And then it's going to have a whole bunch of any characters, and then it's going to have 17 colon. Well, this one has an 18 colon, so that's not going to match my criteria. But this one up here, that one has a 17 colon, so that would match my criteria. All right, so I'm getting very precise. I'm looking for Monday, something that has 17 colon. Oh, and you can see that right here. Uh-oh, I matched something maybe I didn't intend. Error messages that are mod JK error messages that are state 6 error messages. So if I want to fix that 10, we could do something like in front of my hours, there will be a space character, right? And then that eliminates that extra match that I got, right? So I added a little bit of more preciseness. It has to be a space 17 colon, and then a bunch of stuff before the word error in square brackets. All right. So yeah, so like, man, that looks super gnarly, right? But you can see that we just kind of like started from something small and continued to enhance it and build on it to cut down the matches that we weren't interested in, to get more precise, to get the things we were interested in. And as we started to build it out and add on different pieces of it, the regular expression itself got more complex and difficult to read, but all the things that we said are still there, right? Beginning of line anchor, specific text, right? Which we had to use a backslash to escape that square bracket, which normally meant set. Any character wildcard with a multiplier. Exact text. Any character wildcard with multiplier. Exact text. Any character wildcard with multiplier. Exact text, right? And if we wanted to, we could be even more specific and say that that 6 had to occur at the end of the line. In this data, there wasn't a 6 somewhere between mod JK and the end of line. But I can't make that guarantee in all data. So maybe we'd look for state 6 and then our new line character, right? So you can get really precise in what you're looking for. And then you can start feeding more different types of logs into it and get the same data back out again. All right. So yeah, crazy looking regular expressions, and yet it didn't take us long to get here. So that's how regular expressions work and what they do. And then we can do things like help look at logs, do search and replace in files. I actually use this type of analysis a lot when I'm looking at data. So people will send me like giant files of data. Um, Maybe it's the number of hosts we have registered to something, and I export it as a CSV file. And maybe there's, I don't know, a couple 100,000 hosts. But I need to find the hosts that have a specific package on them from this data. And so if I know where that specific package list is in the data, I can then craft a regular expression to say, it doesn't matter what the host name is or what the host type is. I'm looking at this piece of data in this like sea of other stuff to pull out those matches that I'm really interested in. And in fact, things like the Perl language and sed even, this is like what it was designed for, is to like take giant piles of data and filter it out to just the stuff you're interested in. All right, so I think that's where we're going to end for the day. I don't see any unanswered questions in the chat. If you're a deferred viewer, don't forget to drop a like, and please feel free to leave a comment if you have questions. We'll get to them. Next week, let me turn off my screen share here. Next week, Nate will be back. I know you're all rejoicing because everyone loves Nate. And we're going to be talking about benchmarking and rel performance. So we'll talk some about tools that you can use if you want to perform your own benchmarking. And we'll do that in the critical path. We'll cover one. Because I think the more interesting discussion to have is actually looking at other people's benchmarking and figuring out how to read and interpret it, and what's important to look for when you're reading and interpreting benchmark data to know about your system or about whatever the performance of this thing is that the benchmarking is showing you. So that's what we'll be doing for episode 156 next week, is performance benchmarking and benchmark interpretation for Linux. Until next week, thanks everybody for tuning in. Hope you enjoyed regular expressions, and we'll see you next time.